The broadcast is now starting. All attendees are in listen-only mode.
Good morning. I'm Neil Polhemus, head of software development here at Statgraphics. I want to welcome you to the webinar actually, that we're doing today called Multivariate Capability Analysis using Statgraphics. It's a very important topic for those who are involved in quality assurance, particularly when quality depends on more than just one characteristic of your process. Now, I'm going to talk for maybe 45 minutes to an hour, and then we'll have a question and answer period after that. The GoToWebinar program we're using has a facility for you to submit questions, and you can do that anytime during the presentation. I'll wait though till the end of my prepared talk and then answer whatever questions you send. All right, the topic, as I said, of the webinar today is multivariate capability analysis. Multivariate capability analysis is used to demonstrate conformance of a process to requirements or specifications that involve more than just one variable. It's most important when the variables that characterize your process are either not independent, or if those requirements concern the joint behavior of the variables, what happens simultaneously with respect to those variables. This webinar will deal with variable data, that's quantitative data, although attribute data, pass-fail data can sometimes also be considered. Okay, now the outline of the webinar is going to follow Chapter 7 of the book I published last year called Process Capability Analysis, Estimating Quality. It's published by CRC Press, and Chapter 7 deals exclusively with multivariate capability. Now, there are 6 topics I'll be talking about as I go through the webinar. First off, we'll talk about visualizing bivariate data. Bivariate data is obviously a special case of multivariate data where you have 2 variables, but there are a lot you can do visually if you have just 2 variables. We'll then talk about the multivariate normal distribution, which is the fundamental underlying model upon which we'll base our capability analysis. We'll talk about multivariate tests for normality, that is, tests that we can run to find out whether data follow a multivariate normal distribution. I'll then talk about multivariate capability indices, multivariate analogs to indices such as CPK, which characterize the capability of a process. We'll spend a little time talking about multivariate statistical tolerance limits. Statistical tolerance limits give you an interval, or in this case, a region, within which you can be, for example, 95% certain that at least 99% of everything you're producing lies. And finally, I'll spend a little time at the end talking about what we do if we have multivariate data that does not follow a multivariate normal distribution. Now, the example I'm going to deal with has to do with medical devices. I have a sample of 200 medical devices, and each of the 200 devices is characterized by 2 variables. One variable is diameter, and you can see here diameter is required to be somewhere between 1.9 and 2.1. The second variable that characterizes the device is strength, and there's a lower bound on strength. Strength must be greater or equal to 200. Now, what I'm particularly interested in knowing is how many of my devices satisfy both of these requirements simultaneously. at the same time have both diameter between 1.9 and 2.1 and strength greater or equal to 200. Now, if the variables are independent of one another, then you can simply go ahead, do a univariate capability analysis for diameter, do a univariate capability analysis for strength, estimate the defects per million with respect to each of those characteristics, and combine them together. However, if the variables are correlated, particularly strongly correlated, as they might be, devices with larger diameters might be stronger, then you're not necessarily going to get the right estimate of defects per million unless you look at both of the variables simultaneously. Okay, now I've loaded this data into Statgraphics, so let me go over to Statgraphics. This is version 18 that we'll be running today. You see in the first two columns 200 values for diameter, 200 values for strength. I've also created columns with the lower specification limits for the two variables, 1.9 for diameter, 200 for strength. There's a target value of 2 for the diameter and an upper bound for the diameter of 2.1. There's no upper bound on strength, so I've left that particular entry empty. Now, we'll need those columns when we go ahead and do our capability analysis. The first thing that I want to do is take a look at the data. And the best way to look at bivariate data is to go to Statlets, Data Exploration, Bivariate Density. I'll tell it my first variable is diameter, my second variable is strength, and when I press OK, it'll begin by showing me a bivariate histogram. Now, a bivariate histogram divides the observations according to the simultaneous values of strength and diameter. And you can see I can rotate it around to get a different viewpoint. What you'll notice about these variables is there's a strong positive correlation. I think you can see that. Variables with smaller diameters tend to have lower values of strength. Devices with higher diameters tend to have higher values of strength. So it's a good example where you might not get the right answer with respect to process capability if you simply looked at diameter separately from strength, where it's important to actually look at them together. Now, the first thing I might want to do is go up to the toolbar here and ask for a non-parametric density estimator. A non-parametric density estimator will estimate for me the density function of those two variables simultaneously. It's the equivalent of a normal curve looking at two variables. And it's based upon, in this case, a non-parametric estimate. It's basically a window that we pass through values of diameter and strength. And actually, by changing the width of the window here, I could get a little bit more detail if I'm interested. So you can see here, for example, what it estimates the density could be. Now, I can also display it in 2 dimensions rather than 3 dimensions. In 2 dimensions, it's basically an elliptical region, where you see the red on that plot, the density is higher, and then it falls off with the varying colors. I can also ask to display the individual observations on top of the density function. And you can see that the density estimate, the contours here, do a pretty good job of estimating where there are a lot of points, where there are not so many points. Okay, well, let's go back to my 3D plot. That is a non-parametric estimate. Okay, it's basically a smooth value of that histogram. At this point, I have no mathematical model for the data. However, you can see that basically it does look sort of bell-shaped. Actually, multivariate normal distribution, which we'll get to in just a moment, has the property that each of the variables follow a normal bell-shaped curve. And you can see that if I rotate it around this way, well, it's pretty narrow that way, but certainly if I rotate it around here, you get a pretty good idea that there is something close to a normal distribution, probably appropriate for that particular data. Okay. Now, given we've seen that, and I'll go back to my slides here for a moment, it's time to write down a mathematical model for the data. Now, the primary model for multivariate data, the one that is the baseline distribution that we will assume most of the time unless we see evidence to the contrary, is that of a multivariate normal distribution. I've written here the density function for a multivariate normal distribution. It involves a vector variable, x, that's a vector random variable, a vector of means, mu, and if there are m variables, there are m means, and then a m by m variance covariance matrix, which is normally called sigma. Okay, in just a moment, I'm going to fit that particular distribution to our data, graph it out for you. There is an important property, though, of the multivariate normal distribution that comes in very handy. And that is that any linear combination of the m variables follows a univariate normal distribution. Now, that includes the variables taken by themselves. It includes the sum of the variables, the average of the variables, any linear combination of the m variables, if you plot it, will follow a univariate, one variable normal distribution. Now, in the case of the bivariate normal distribution, which is what we want to use for our medical devices, a bivariate normal distribution has two means, mu1 and mu2, two standard deviations, sigma 1 and sigma 2, and a correlation coefficient rho, which most of you are familiar with from regression analysis and so forth, which is somewhere between -1 and 1. We could also parameterize it with a covariance instead of a correlation, but in the case of two variables, I like to think about the correlation, because we're all familiar with that. A positive value for rho indicates positive correlation between the variables. A negative value for rho is a negative relationship between the variables. Now, if I go back to Statgraphics, I can click the radio button here that says normal distribution, and you will see a normal distribution, a bivariate normal distribution, fit to this particular data. It's very similar, of course, to what we saw in the case of the nonparametric estimate, but in the case of the multivariate normal distribution, the contours are ellipses in the space of diameter and strength. Okay, now that bivariate normal distribution is going to be the model we want to use to estimate process capability. However, before we do that, we really need to go and do a test. We need to do a multivariate test to see whether the multivariate normal distribution is appropriate for this particular data. Now, the most widely used test to test for multivariate normality is something called Royston's test. Royston developed a test statistic which he called H that combines the Shapiro-Wilk W statistic for each of the m variables in the data set. So in this case, it would take the W statistic for diameter and the W statistic for strength, combine them into a single statistic, that will tell us whether or not the two variables together come from a bivariate normal distribution. Now, it turns out that H can be referred to a chi-square distribution with degrees of freedom that actually depend upon the correlations amongst the variables. That's a little bit unusual. It's not a fixed number of degrees of freedom. The degrees of freedom actually depend upon how strongly the variables are correlated. Now, to do this in Statgraphics, what I'll do is I'll go back to where I had my data, back to Statgraphics, and go to Describe, Multivariate Methods, Multivariate Normality Test. On the data input dialog box, I'll put the two variables I'm interested in, diameter and strength, and it will go ahead and run Royston's test. Now you can see up at the top of this analysis summary here that there are two means and two standard deviations, one for diameter, one for strength. You see the correlation matrix, and they're quite strongly correlated, diameter and strength. There's a correlation of above 0.9. The tests for normality are a little lower on my analysis summary. You see the Shapiro-Wilk test for diameter, the Shapiro-Wilk test for strength, and Royston's H statistic. In the case of the Shapiro-Wilk test, values less than 0.05 would cause me to reject the hypothesis that a variable followed a normal distribution at the 5% significance level. Similar thing happens here with Royston's test. If that p-value there is less than 0.05, then I would declare that the data did not follow a normal distribution at the 5% significance level. So basically, I'm going to feel that the multivariate normal distribution is a reasonable model for my data as long as that p-value is above 0.05. 0.7, of course, is quite a comfortable p-value, indicating that jointly diameter and strength may well be modeled by a normal distribution. Now, like most statistical tests, I haven't proven multivariate normality. However, there is no reason to reject that particular hypothesis. This incidentally works for any number of variables. I'm using two in my example here because it's just a lot easier to visualize what I'm talking about with respect to multivariate normality. Now, we also have a graph over here, something called a chi-square plot, which can also be used to test whether or not data come from a multivariate normal distribution. What it does is it takes the squared distance of each of my data points from the centroid of the data. Basically, in this case, I've got my bivariate normal distribution. The chi-square plot takes each of those points, finds the distance to the centroid of the data, which is right in the middle of the ellipse there, in a standardized sense, though. Before it measures those distances, it stretches mathematically those ellipses to compensate for the fact that they have different standard deviations and basically they're measured in different units. Okay. The important thing about the chi-square plot, though, if the data come from a multivariate normal distribution, then these normalized square distances should follow a chi-square distribution. And what we've done is we've taken each of the 200 observations, plotted the empirical cumulative distribution function of those 200 points, and added to it what are called 95% Kolmogorov-Smirnov limits. There's also a Kolmogorov-Smirnov test applied to the data to tell us whether or not the data follow a chi-square distribution. Over here it says that according to the Kolmogorov-Smirnov test, the p-value is greater than 0.25. We interpret that similarly to the way we'd interpret the p-value on Royston's test. Anything greater than 0.05 says that the multivariate normal distribution may in fact be a reasonable model for our data. Okay? Now, according to this multivariate normality test, I'm reasonably certain that I can just go ahead and use the multivariate normal distribution as a model for the data. Given that that's the case, I now want to calculate some capability indices. The point of a capability analysis is to determine what percentage of the product that I'm producing falls within the specification limits. In the case of univariate data, if I had simply one variable, most of you are probably familiar that we can calculate things called capability indices that help summarize how well that process does meet a set of specification limits. Now, the most widely used index, capability index, is something called CPK. Okay, CPK measures basically how many standard deviations separate the process mean from the nearer specification limit. If I have both an upper and a lower specification limit, then CPK is the minimum of the mean minus the lower spec divided by 3 sigma, and the upper spec minus the mean divided by 3 sigma. Basically, you look at the distance from the mean to the specs, find the spec that's closest to the mean, divide it by 3 sigma, and you get CPK. That's how you do it when you have a single variable. Now, we can also write CPK as Z min over 3. Some people like to use CPK. Some people like to compute Z-scores instead. In that case, Z min is simply the minimum distance from the mean to the specifications divided by sigma. Not 3 sigma, just sigma. So depending upon which you like to use, you can use Z-min or you can use CPK. Now, what I want to do is now extend that definition to the multivariate case. Okay, I'm going to do it like this. Let's assume that the variable of interest follows a univariate normal distribution for the moment. In that case, the probability that you get an observation more than Z-min standard deviations from the mean is calculated by 1 minus the cumulative standard normal distribution at Z-min. So if I know Z-min, I can calculate the probability of being out of spec, or if I know the probability of being out of spec, I can calculate Z-min. Now I say approximately equal to because if you do have both an upper and a lower specification limit, this particular formula is neglecting the second limit, the larger value of Z. In most practical cases, one Z will be considerably larger than the other. You may be off-center to the left or off-center to the right, so that one or the other of the specs dominates the probability of being out of spec. So we get a reasonable approximation for the probability of being out of spec if we take 1 minus the cumulative standard normal distribution evaluated at Z-min. Now, if we combine everything I've shown you up till now, it turns out that we can then approximate CPK as being 1/3 the inverse standard cumulative distribution at 1 minus theta, where theta can be calculated from Z-min. So if we know Z-min, we can calculate theta, and if we know theta, we can calculate CPK. Now, how are we going to use this? Well, I'm going to use this to define something I call a multivariate CPK. I'm going to call the capability index MCPK. I'm going to set it equal to Z-min divided by 3. But in this case, Z-min is going to be the value of a standard normal distribution which is exceeded with probability theta, and theta is the probability that a vector of random variables is outside the region defined by the specification limits. So basically, I'm going to do this. I'm going to take the requirements of my M variables, and I'm going to take my fitted multivariate normal distribution. I'm going to calculate the probability of jointly being outside the specification regions from that multivariate normal distribution. So I'll get theta by finding out how much of the multivariate normal distribution is outside of the specs. From theta, I'll calculate Z-min, according to what I had on the previous slide. And then from Z-min, I'll calculate my multivariate CPK. Okay, now that may be more confusing than it really is. So let me go ahead and show you how it's done in Statgraphics. I'm going to go in Statgraphics now to SPC Capability Analysis, Variable Data, Multivariate Capability Analysis. I'm going to put in the data field diameter and strength. Those are my two variables. Could be more than two, but I just have two. I'm going to take the column USL and put it where it says upper specification limits. I'll take the column nominal and put it in the nominal field. Take the LSL column and put it in the lower specification limits field. I'll then press OK. I'll ask for capability indices and the capability ellipse. Okay, now what has it done? Well, the first thing it's done is it's fit a bivariate normal distribution to the data. Okay, and you can see I apply the bivariate normal distribution. The blue area is the area within the specs. The red area is the area beyond the specs. It's also calculated at the top DPM equals 2.21754. That's the area of the bivariate normal distribution beyond my two specification regions. Okay? In other words, I estimate that 2.2 of my medical devices, 2.2 per million, are likely to be out of spec with respect to one of the variables or another or both. Okay? Now, I also like the plot down here called the capability ellipse. This capability ellipse shows me where 99.73% of the bivariate normal distribution lies. That would be the equivalent in the univariate case of plus and minus 3 sigma. In the bivariate case, the 99.73% containment ellipse is an ellipse within the space of the two variables. You can also see the specifications here, 1.9 to 2.1 for diameter and greater than 200 for strength. Now, if I go back to the summary here, to the analysis summary, it'll also show you here how the joint defects per million compare to the individual defects per million. If you look at the estimated DPM for diameter, it's 1.54 defects per million. If you look at the estimated defects per million for strength, it's 1.236 defects per million. The joint estimate is 2.217. You'll notice the joint estimate is quite a bit smaller than the sum of the individual estimates for diameter and strength. That's due to the strong positive correlation between diameter and strength. It turns out that there's a reasonably high probability that if a variable is out of spec with diameter, it will also be out of spec with strength, both at the same time. So if you were to take the individual defects per million and add them up, you'd overestimate the total defects per million. Now that's, I think, the real importance of doing a multivariate capability analysis. The fact that we're handling the joint behavior of diameter and strength, not just looking and summing the univariate estimates. Now there's also one thing I wanted to show you down here. It's the estimate of the defects per million, but also the estimate of MCPK. Once I know the joint defects per million, I can estimate Z-min. Turns out to be about 4.6. And I can also estimate MCPK. It turns out to be 1.53. I can also estimate a multivariate statistical quality limit, what I call the SQL. If you take the Z-min and add 1.5, you get what the Six Sigma people like to use. Actually, I'm sorry, it's not the statistical quality limit, it's the sigma quality level. I had a slip of the tongue there. I can see the Stat Advisor, though, talks about it. It's one good thing about the Stat Advisor. It knows what SQL stands for. The sigma quality level is Z-min plus 1.5. It is in excess of 6. So according to the Six Sigma folks, we are operating at world-class quality. Right? Anything above 6 is world-class quality. Now, the interesting thing about that SQL, it takes account of both diameter and strength and their joint behavior. Now, if I press the right mouse button and go to Pane Options, I can also ask for lower confidence bounds on all those capability indices. That'll take a moment to do. What it does is it uses bootstrapping, which is something I can talk about in another webinar. Bootstrapping, though, subsamples the data we have to give us lower bounds, 95% lower bounds on those statistics. I'm 95% confident that MCPK is at least 1.4. I think it's 1.53. It's at least 1.4. We get a lower bound on the sigma quality level at 5.72. a lower bound on Z min, it's 4.22, and an upper bound on defects per million at 12. Best estimate of the defects per million is 2.2. And in terms of the sigma quality level, in terms of the defects per million, an upper bound of 12. What graphs are not showing? Good. Okay. I'm told that my audio was a little bit behind on one of these graphs. We have a large audience today, in fact, considerably larger than normal. So I'm afraid that perhaps my audio is not coming through, or perhaps is a little bit behind my graphs. Just to review, that is the capability ellipse, which shows where 99.73% of my, well, not my observations, but all the values from that bivariate normal distribution are estimated to lie. That ellipse is the equivalent of plus and minus 3 standard deviations. Okay. If there were some graphs which did not, which came through well after my audio, you'll have to tell me at the end of my presentation. We can go back and look at some of those if you want to. Okay. Well, that is a multivariate capability index. It's CPK. Another important topic I wanted to talk about was something that's becoming more and more popular these days when people are doing capability analysis, and that is the calculation of statistical tolerance limits. You may be familiar with calculating statistical tolerance limits for a single variable. You take the average plus and minus something called K times the standard deviation. There's an equivalent in the multivariate case. A multivariate statistical tolerance limit contains a specified percentage of a multivariate population at a specified level of confidence. I can say, give me a region within which I'm 95% certain I'll find 99% of what I'm producing. Okay. So, but it's a multivariate. So we can say, give me an interval, actually a region, with at least 99% of all my multivariate observations with 95% confidence. And as is the case with univariate statistical tolerance limits, if the multivariate statistical tolerance limits are completely within the region defined by the specification limits, then we know that at least 99% of all multivariate observations jointly satisfy those specifications. Okay, now, how do we calculate multivariate statistical tolerance limits? Well, there are two ways to do it. There's an exact way to compute multivariate tolerance limits, and that's to construct an elliptical tolerance region using the fitted multivariate normal distribution. Okay, I'm going to show you that in just a moment. You can also, though, construct separate confidence limits, or separate tolerance limits, I probably should have said, for each of the variables, adjusting each set of limits using a Bonferroni approach. For example, let's suppose I want a region that contains at least 99% of my variables' diameter and strength. I can do a tolerance region for 99.5% of the observations with respect to diameter, and a separate 99.5% region for the other variable, strength. Okay? So I can construct a region where I miss 0.5% with respect to strength and 0.5% with respect to diameter, okay, and know that I have at least 99% of the observations in a joint sense. Here, let's go ahead and take a look at that. You'll see it's fairly easy to do. To do it, I need to go to Describe, Numeric Data, Statistical Tolerance Limits, Multivariate Tolerance Limits. I'm going to put in diameter and strength. Those are the two variables for which I want the limits. The next screen, I can specify my level of confidence and the proportion of the population I want to bound. So I can tell it, for example, I want to bound 99% of the population with 95% confidence. It's not. Okay. So basically, I've put in my two variables, diameter and strength. And on this screen here, I put my level of confidence and my population proportion. I then need to tell it which of my variables have two-sided specifications, which of the variables have a lower bound only, and which have an upper bound only. There's a two-sided specification interval for diameter. Strength, on the other hand, has only a lower bound. Once I do that, I can then ask for the output that I want to see, and it will calculate for me the multivariate tolerance regions. Now I'm being told that my screens are somewhat behind. Well, tell me when this screen comes up. I apologize for this. We're running a little slowly. Okay. Okay, it looks like the internet's finally cooperated with me. It did take a couple moments to do those multivariate tolerance regions. It has to do a numerical integral in the space of diameter and strength. So there is actually quite a bit of calculation that's required in order to do it. Okay, so just to review what I did, okay, I had entered into the data input box diameter and strength. I had indicated that diameter had two specification limits and strength had only a lower bound. What is calculated for me down in this particular region, down near the bottom of the analysis summary, are 95% simultaneous Bonferroni limits for 99% of the population. Using the Bonferroni approach, I can tell you that at least 99% of my population has a diameter between 1.93999 and a 2.05917. And at the same time has a strength no less than 221.895. Those are simultaneous tolerance limits for 99% of the population. I've also graphed in the upper right corner both the Bonferroni tolerance limits and the exact elliptical tolerance limits. The square region, which has a lower and upper limit for diameter and simply a lower limit for strength, is the joint 95-99 Bonferroni limits. The ellipse on that graph is the exact 95-99 joint tolerance region for both strength and diameter. Now, one thing you can notice is that there are areas within the Bonferroni limits which are not within the elliptical limits. At the same time, there are points within the elliptical limits that are not within the Bonferroni limits. This point right here, which turns out to be row 150 in my data set, is outside the Bonferroni limits, but well within the exact tolerance region based upon the bivariate normal distribution. Now, that works well, of course, if you have two variables. If I had three variables, the exact tolerance region is an ellipsoid in 3 dimensions. A little harder to plot. In that case, we have to rely on the second plot that I created and the bottom right-hand corner, which was the multivariate distance plot. The multivariate distance plot measures the distance of each point to the ellipse or ellipsoid if it was more than 2 variables. It's that standardized type of distance that I was talking before. There is a point on this plot for each of the 200 medical devices in my sample, showing the scaled distance from that point to the center of the ellipse, or the center of the ellipsoid if more than 2 dimensions. If you are more than 10.664, you are beyond, outside of the multivariate tolerance region. Okay, now you can see that all of the points, in fact, are within the tolerance region. This is the point, I believe, oh, that's 0.97. This over here is 0.195. This is 0.126. Actually, none of those are the ones that were outside the Bonferroni region, because the most extreme points with respect to the elliptical tolerance regions are this point here, number 97, and this point here, number 126. Okay, the nice thing about the distance plot is I can identify whether or not all of the points are within the elliptical distance, and for any combination of the variables, I can calculate that distance, and if it's bigger than 10.664, it is outside of the multivariate tolerance limits. Okay. I hope my slides are catching up with the audio here. Incidentally, I'm going to make the slides available on our website after I finish talking, and we're also recording the webinar, so you can look at it again with slides in hand if some of what I've talked about so far is not totally clear. Okay, so there are two methods anyway, a Bonferroni method and an exact elliptical tolerance region that you can calculate from the multivariate normal distribution. Now, there's one more topic that I wanted to talk about before I stopped, and that is, what do I do when I have multivariate non-normal data? What do I do if I have 2 or 3 variables that I want to look at jointly, but they do not follow a multivariate normal distribution? Well, there are other multivariate distributions, but they're even more difficult to deal with than the multivariate normal distribution. We find out that in the case of multiple variables, the best approach to handling non-normality is usually to transform one or more of the variables. Now, what we want to do is we want to do something similar excuse me, to a Box-Cox approach. The Box-Cox method is something we use to transform a single variable, which looks for a power transformation that makes the distribution of the variable approximately normal. Excuse me, got a little cough here. We can also, though, so we can do the Box-Cox method similar. Look at diameter, try to normalize it, look at strength, and try to normalize it. There's also a multivariate power transformation, however, which will find jointly the powers of all the variables, the best powers that maximize the joint profile likelihood. Okay? Now, let me just demonstrate this for you. Let me close off this particular data file and open up a second data file. I have a second data file with actually 2 columns of random numbers that I've generated from a log normal distribution. Okay? And I'll wait a minute till they show up on the screen. Okay. I'm told that you can now see the data. This is 2 columns worth of data, X1 and X2, both of which are random samples from a log normal distribution. Now, let's suppose I went to describe multivariate methods, multivariate normality test. Told it to look at X1 and X2. When that output appears, you can take a look at Royston's H statistic. And see whether or not those data jointly follow a normal distribution, a multivariate normal distribution. Down at the bottom of the page, when it appears, you'll see a table. It says normality tests. Right about here, you'll see in red the p-value for Royston's H test. The p-value is 0.0000. That is a very strong rejection of the idea that those 2 columns come from a multivariate normal distribution. If I go ahead now and push the right mouse button and ask for analysis options, I'll be given the opportunity, if I want, to determine a transformation of the variables. I can tell it that I'd like to transform each variable separately using the Box-Cox transformation. Or I would like to determine, using the multivariate power transformation, powers to apply to both x1 and x2 that maximize the joint likelihood profile. Now I can also tell it that I'd like to try adding something to each of the variables, x1 and x2, which I'd have to do if, for example, I had values, some zeros in my data set, because it's going to try power transformations that require positive data. Once you do that, it'll go ahead and estimate what the best transformation is for each of the variables. You'll see the output modify, and it will show you a section where each of the variables has been transformed according to taking it and raising it to a power. In this case, it says the optimal power for x1 is minus 0.08. The optimal power for x2 is 0.07. Now, both of those powers are quite close to 0. 0 corresponds to a log. So, given the fact that I generated these randomly from log normal distributions, you see it's doing a pretty good job of determining what power transformation would normalize the data. Okay? And then I can take the data raised to those powers and do my multivariate capability analysis on those transformed values. Okay. That was the last prepared example I had. I will, sometime this afternoon, post on our website the Statfolio I created here during the webinar, and also the data files, so that you can go ahead and try it yourself. I'm also going to show you a slide here where you can find information about the book I published, Process Capability Analysis Estimating Quality. It's published by CRC Press. We have a page on our website that gives you information about it, shows you the table of contents, allows you to go to the CRC website if you'd like to get a copy of the book. Okay. All right. Now, I've been told that because of the delay in some of these graphs appearing, you might want to see one of those examples again. If you could indicate to me by sending in a question that you'd like to see a particular example again, I can also do that. Let me see if there are any questions that were submitted that I should take a look at. Just hang on here a minute so I can get myself into the section where okay. One of the questions that was sent in, it says if one variable has a large standard deviation and a second variable has a small standard deviation, doesn't this mask the dependency between the two variables, And in this case, there's no value in using multivariate analysis. Now, I don't think it's the magnitude of the standard deviation that matters, because everything is going to be normalized here by taking the data and dividing by its corresponding standard deviation. Where multivariate analysis is important, it depends more on the dependency, on the extent of the correlation between the variables. Because it really depends upon whether or not there's a measurable probability that an item might be out of spec with respect to both variables simultaneously. If the variables are not related to each other, and we're talking about defects per million, the chance that one variable is going to be out of spec with respect to more than one, that one item will be out of spec with respect to more than one variable at the same time, is very small. But if they're highly correlated, then there's a distinct chance that if you're out of spec, for example, with respect to diameter, you might also be out of spec with respect to strength, and we don't necessarily want to double count you as being a defect. So I would think that it's not the standard deviation that matters, it's the strength of the correlation. There was another question asking whether the book that I wrote requires Statgraphics to understand the material. It does not require Statgraphics to understand the material, and some of what's covered in the book can be done using other software. What I've talked about today, though I'm not familiar with being in any other program. All this multivariate capability analysis is material we added to version 18 because it wasn't available anywhere else. So with respect to the standard capability analysis, univariate multivariate analysis, you could do that using other programs. But when I talk in Chapter 7 about the multivariate statistics, it would be more difficult. There's also a question, can Statgraphics 17 be used for multivariate tests? Version 17 has an earlier version of the multivariate capability analysis, where it estimates defects per million from multivariate data. It does not do the multivariate tolerance limits. It does not do the multivariate normality tests. Those were all new in 18. There's also a question, since process capability assessments only make sense for stable processes, do you suggest assessing assessing stability using a multivariate control chart, or assessing stability with regular univariate charts separately? Well, the answer is I'd rather you did a multivariate control chart. Statgraphics contains two multivariate control charts. One we call a t-squared control chart. The second, a multivariate EWMA chart. Now, the multivariate t-squared chart does something very similar to that distance plot. It calculates from a cloud of data the scaled squared distances from each of the points to the centroid of the data. And it'll put the equivalent of a 3 sigma limit at the top of the control chart. So it looks very similar to that distance plot I showed you before, except it's not a tolerance limit that it puts up there. It's a 99.73% control limit. But yes, I would think that if you wanted to assess stability of multivariate data where the variables are themselves highly correlated, it would be a good idea to do a multivariate control chart. Now, some people like to do control charts on each variable separately in addition to the multivariate t-squared chart. That sort of gives you the idea of not only am I out of control with respect to the variables simultaneously, but also am I out of control with respect to each of the individual variables. Okay, there's a question, how do you assess correlation of variables? How would I assess correlation of variables? Well, there is a procedure in Statgraphics under, I guess it's relate, that does calculate pairwise correlations amongst the variables. So you can go there and it will actually calculate a correlation coefficient. If I go back, for example, to Statgraphics, let's see if I can go back to Statgraphics, and hopefully in a few seconds here, my screen might appear on your screen. Let me just call up that data I had on diameter and strength. If you go to the top menu to relate, multiple factors, multiple variable analysis, you'll see that at the top. This will actually calculate the correlations. I can ask for diameter and strength and have it calculate a scatter plot matrix and also something that I call a correlation plot. This particular plot is quite helpful when you have multiple variables. It will calculate the correlation between all pairs of variables and will also shade a particular cell according to the magnitude of that correlation. So a good place in Statgraphics to look at the correlations is to go to relate on the top menu to multiple factors, multiple variable analysis, and do the correlation plot. Okay, let me see what else we might have here. I'm told there's one more question that would be useful to answer. There's also a question about whether this can be applied to non-manufacturing processes. Absolutely. Capability analysis is something that applies to any process where there are requirements. Now, we did it in this case with respect to variable data, where we're taking measurements. But you know, that could be the measurement of a waiting time at a post office. And you might have a requirement that the waiting time at the post office be no more than 5 minutes. So certainly with respect to service industries, there are a lot of examples. I know there's a lot of examples out there where capability analysis is applied to hospitals, where they look at, for example, the frequency of falls or infections or things like that that occur in hospitals. So there's lots and lots of applications of capability analysis beyond manufacturing. A lot of us use manufacturing examples because that's where a lot of it initially was developed. But certainly we could do the same thing for service industries. All right. As I said, it is my intention to post on our website both my slides, the data sets, the Statfolio I created, and of course the video. We've recorded this webinar. We will be putting it on the internet for you. So give us till sometime this afternoon. Go to statgraphics.com, go to the top, somewhere on the menu, I think it's under Learn, you'll see a link to webinars, and all that information will be placed on the website for you. I apologize for the delay. We had actually many more people attend this webinar than have attended most of the webinars in the past, and we may have a few technical details we'll have to work out for the next webinar. Incidentally, this is the first of what I hope will be several webinars this fall. Now that everybody's back from summer vacation and so forth, it's a good time to talk about topics like this. Any other questions you might have, just send them to support@statgraphics.com. Any comments you want to send to directly to me, you may. Neil, Neil, at statgraphics.com. We'll take a look at all those. Otherwise, thank you and have a good day.